I'm John Lea-Cox. My title is Nursery and Greenhouse Extension Specialist. I've been at the University of Maryland for 20 plus years, and it's because of the team that I'm here, and not because of me. So, on behalf of all of them, just to tell you a little bit about our tools and methods that we've been developing, just an outline of my talk. I'm going to go through it fairly fast, so hold on to your hats. So our toolbox that we've developed and are continuing to develop, and as part of that it's hardware, and I'll show you a little bit about the hardware, but most of what I'm going to talk about is where we're going on software development, because there's no doubt in my mind that predictive model capabilities, artificial intelligence, machine learning, it's all going to be a big part of this future. And more importantly, for the farmers in the audience, economic impacts, because that's the bottom line on a lot of this stuff. So I hope to cover some of that, and maybe give you a little bit of an example of some of the tools and strategies that we've been developing and helping farmers with, particularly frost monitoring. So kind of a graphic. I like to put this up because we're all, as scientists, very good on data and moving data into information, and then it stops. So once we got the information, we publish, and then it just disappears into this black box. Well, unfortunately, that's not very useful. And so what I'm really about is transforming information into knowledge, and more importantly, knowledge into action. Because as an extension specialist, I like to think I'm all about action and not so much about the preceding part of it. Now, if you think of the system that we're building, this is the system that we're building on the ground. So this is marrying what I've got on the top with what we're building in terms of infrastructure. Software is very good at getting data into information. You can graphically represent it. It can be good at actually getting into the analytical tools, so you can get some analysis. We need a lot more work in terms of predictive modeling capabilities, particularly predictive, not past. We're very good at looking at the past. We're not so very good at looking at the future. And more importantly, how do we get that embedded intelligence then communicated, and for what I like to call a 5-minute decision window. It's when you sit down with your cup of coffee in the morning, Pam, and you've got that decision to make. What's the information that's going to make you make that decision better for you? Okay, so lots of ways to put stuff together. I'm not going to spend a lot of time on this, but this is just some of the hardware that we've got. It's easier to do it without a picture rather than a graphic, because what we've got is hardware, nodes, and radio loggers, and they communicate in different ways. But basically, we're just building networks of sensors. Some of them sensors are ground-based, soil-based, but we've got a whole range of sensors, which I'll show you, that are basically tying all sorts of information together. More importantly, we're now really going to the cloud. And this is the future when we get into cloud-based systems, because that unleashes our potential to then really go wide scale rather than just farm scale. Okay, hardware. These are just little different flavors of nodes. We call them nodes. They're radio data loggers. They literally just gather data, they hold data, and they transmit data. And this is on the right-hand side is just a flavor of that particular node, which goes straight to the cloud. It just basically goes through the cell phone network. We connect these to various types of sensors. So there are lots of different sensor companies out there. Just a word of caution, you typically buy, let me see how I can phrase this diplomatically. You buy is what you get, right? So if you buy cheap, you're going to end up with probably poor quality data. And there's no point in buying a cheap sensor, $20 or $30 less cost sensor, when that sensor is going to be giving you data for the next 5 years. It doesn't make any sense. So don't buy cheap. There are lots of good companies out there that are producing all sorts of different sensors. They tend to sell each other's sensors. It's an interesting business, but if you have any questions about that, I'm happy to answer them. These are important. These leaf wetness, sonic anemometer, temporal humidity, they're very important because I want to really get to the point where we start talking about precision of data. I love my folks at NIWA. They're doing a fantastic job, but we've got to get beyond a weather station at airports that is 10 kilometers away from a farmer. You're not getting the data that you need to. Okay, so lots of ways that we can put this together. This was the project that I showed you with the big team. Basically what we did was we put a control node capability together that we can now automate irrigation based on on soil moisture sensors. The big take-home lesson from this was that repeated, and I'll show you some slides, repeated studies showed that machines make way better decisions than humans. Way better decisions than humans, and we're very good at turning the tap on, but we have no idea when to turn the tap off. And so all of the efficiencies that we gained, and I can pretty confidently say that I can go onto any farm, and I'm pretty sure that I can save a farmer at least 50% of the water that they use just by giving them the information to turn that valve off. Because we're all conservative, and we really just don't know what's going on underneath our feet. Okay, so lots of ways we do that with the software. This is just some of the software we developed as part of that project. The most important thing is that these systems now start actually working with biological and seasonal changes. And just to explain this graph a little bit, it looks very curious, I'm sure, but the little squiggly lines are basically soil moisture. It's a very gross set of data because it's zoomed out to 3 months. The bars are actually irrigation time. So this is actually from a block of trees. They're ornamental trees, and this is when they leafed out over spring. And it's a very difficult crop to work with because basically we're always over irrigating in the spring when we don't need to. And what this shows is how the frequency of irrigation automatically increases as that tree leaves out, as it starts growing, as it starts demanding more water, then the whole system feeds back and actually feeds back into that irrigation decision. This is not manually driven. This is not driven by the farmer. This is all machine driven. It's all basically sensor driven. Okay. So, bottom line to that study, about 3 times less water in that particular case that we applied to this particular crop. When we looked at return on investments, this was a whole network. It was a whole another paper that we did with Eric Lichtenberg, one of our economists. I love Eric. He's fantastic. He makes my day with all of these numbers. But basically what we showed was that the plasticity of cost of a network is entirely dependent on what you pay for water. So this is based in Tennessee, cheapest water in the country. They're pumping out of a river, perennial stream. The only cost of their water is literally their energy pumping costs. However, we did an exercise where we went to $3 a thousand gallons. That was about California water costs at that point. So you can see how that 2.7 year return on investment with a $50,000 network dropped to a 4-month return on investment just on the price of water. Okay, thanks. So I'm going to skip through some slides. So lots of other things about reductions in benefits and quality and all sorts of things. Basically, these gains in economic benefits are multiplicative. So water leads on to quality, quality leads on to reduced production times. you can't look at gains just in a single sense. Planetary boundary layer. This is my question this morning. Part of the paper that David and Art put together this last year, and I was a little small part, was about this phenomenon. And this one scares me, because this is about how we are not measuring, and this gets to my point about precision, we're not measuring the planetary boundary layer with most of our climate models. And when it comes down to this particular paper, it's all about how night temperature is probably going to be double the global daily average temperature. Now, that's why, but this is the outcome, because night temperature is going to have devastating effects on our perennial crops. I hate to say it, Pam, but night temperature is going to cause you a lot of problems in terms of apples, in terms of yield, in terms of respiration, in terms of pollination, let alone all the water and everything else. So this is where I think we should be really focusing our efforts. We need to be starting to look at the knock-on effects of climate change, because it's just like the economic analogy I just walked you through. It's not you can't look at these things in isolation. You have to look at them in terms of the compound interest on factors. So this is how we're doing it with the weather stations. I've got various ways that we can do this. I'm very excited about the new capabilities that we're doing in terms of the cloud software we're developing. This is just one of the tools that I'm using called AgZoom, but it allows you to actually geolocate weather stations and nodes at any level of precision. You can literally go down. This is some of our networks. You can go down to the farm scale on this. Now, most importantly, that's now giving you site-specific data from your farm. This is the point about weather stations being at an airport. I work with farmers who've got a 300-foot elevation change between the top of their farm and the bottom of their farm. And I know from frost monitoring, and I'll show you because I've got to speed up, but in terms of frost monitoring, we are now seeing probably a 3 or 4 degree Fahrenheit temperature difference between the top field and the bottom field. So how are we going to ever understand risks and threats when we're not measuring at the level of precision that we need to be? The good news is that these tools are now cost effective. A weather station is probably going to cost you $3,000. Software like this is probably going to cost you $100 a year. So this is not only giving you data on temperatures, you can put your own networks together, and basically what you're now doing is getting real-time data. And the point being is now you can actually get to this data where you're looking at temperature, and this is some of the temperatures under row covers. Oh, I beg your pardon, I got through it too quickly, I think. Sorry. But radiation, this is the frost monitoring. So this is the frost monitoring we're doing with strawberry farmers. We're actually monitoring in the canopy. So we're not only getting from the farm weather station, but we're now putting sensors where they matter, which is actually in the canopy. And there's a lot of variability in terms of data and precision just between the crop canopy and a weather station standing out in the field. So now when we marry this with other adaptation, strawberry farmers use row covers, and what we've been doing is helping farmers understand by placing sensors underneath row covers as well as in their weather station, they now have this real-time data delivered to their phone at 3 o'clock in the morning where they can make a rational decision whether they've got to turn that irrigation system on, because it's the irrigation system that is giving them the frost protection. But they don't want to turn an irrigation system on at 3 a.m. on a spring morning, because when they turn that on, they can't get their tractor into the field for the next 4 days. Okay, so that was a near miss last year with a farmer that we've been testing this capability with in South Carolina. If you remember, 14th, 15th, and 16th of March last year, but it wasn't a nice couple of days. Even down in South Carolina, we lost a lot of peaches. But this is where we're going. We're going to risk management. Farmers are the ultimate risk managers. They deal with risk every day, and what I'm hoping that we can do a much better job in the future is give them the tools that they can have that information that is site-specific, that they can just make better decisions for their own farms based on their own data. And I'll leave it at that. Thank you.
Sounds like you work mostly with horticulture producers, as you should based on your job description, but do you work with field crop people?
Well, what we've been trying to do is, and I'm an ornamental guy, so I tend to work with field producers of tree farmers and greenhouse growers, so I'm protected as well as open culture. What we've really been trying to do, though, is in building these technologies is not to think about crop-specific solutions. Because ultimately, we want to build a technology that could be applied to any crop. And build it at a scale and at a price point where you can start small. You can start with 1 or 2 nodes that'll cost you $3,000–$5,000. You can test them out. You can move them around. You can put them where your problems are, and then you can build your networks over time. You're not locked into this one kind of size-fits-all solution, because no solutions fit all, unfortunately. Pam.
But then the question is, when you have all this data and you know that your temperature is going up and down, whatever, then you need to have some advice as to what that means.
Sure, and that gets to the question this morning, I think, about extension specialists, because I don't think we need more IPM scouts who are out there doing scouting. My philosophy is, I think we need to be teaching you and giving you the tools to be able to actually make those decisions yourself, because ultimately you're probably scouting yourself anyway.
Well, if we had a computer program that listed the options.
And that's the predictive.
And we can go back and say, was it really this degree that we had to worry about, or was it that?
Oh, I didn't mention that. That's the alerts. So you get alerts, and then you can always go back and look at the data. So you're getting 5-minute resolution data every 15 minutes through the cloud, delivered to your cell phone. So you can actually check your temperature at 3:30 and say, oh, well, I'm getting to 35, but it was 36 an hour ago, so I guess I better get in the truck and start turning those valves on. Yes?
Yeah, I'm interested to ask you. Day temperature, increasing day temperature is better than increasing night temperature?
When a lot of the science is focused on daily average temperatures, and I'd encourage you to read all of the papers that came out just this last month. They were, wow, that's an incredible set of papers. What I'm talking about is the paper that David and Art took the lead on, and it identified as night temperatures, the increase in night temperature, particularly in summer, increasing at twice the average. So instead of getting a 4-degree Fahrenheit increase in daily average, we're probably going to see an increase in probably 6 to 8 Fahrenheit in night temperatures. Okay, thank you.